My name's Ryan, and today I'm going to talk to you about energy. Energy is the property of matter that makes things move or change, makes things go, grow, and it's the ability to do work. Now, there are a couple different types of energy. First, I'm going to talk about kinetic energy. Kinetic energy is defined as the energy of things in motion. Anything in motion has kinetic energy. If I take this band and I fling it across the room, it had kinetic energy because it was moving. If I take my phone, flip it a little bit, if I take the quarter, and I flip my quarter, it has kinetic energy. It's moving. Now, there's another type of energy, and it's called potential energy. Potential energy is stored energy. Right now, my quarter is in my hand. It has potential energy. But if I drop it, turns into kinetic energy, transfers into kinetic energy, but once again, potential energy is stored energy. Everything has it. It has the energy because I put the energy in there. Sounds a little weird, but it's true. It was on my table, and if I go over and I pick it up, I'm doing work. As I said before, energy is the ability to do work. So when I do work, I put energy into this system of energy. System of energy, right in this case, is the phone. Pick it up, I'm putting energy into the phone, and then it's stored right here. Now, some of you may be a little confused by the prospect of the word work and how I used it. Some of you think that work is when you go to your job and you do your work and you get paid. But when you're talking about energy, it's a little different. Work is applying an unbalanced force over a distance. So, it's the same. Like, an unbalanced force is pretty much just exerting energy. If I pick anything up, I apply an unbalanced force in that. And I do that work to pick whatever I'm picking up is. It could really be anything. If I pick anything up, it's just work. Or if I move anything, if I change anything. I was sitting here in my chair. Take my chair, move it, applying unbalanced force over a distance, and doing work in turn. Now, moving on to temperature. Temperature is defined as the average speed of all the molecules in a material. The higher the temperature is, the faster the molecules are moving on average. The lower the temperature is, the slower the molecules are moving. For example, I'll show you my thermostat. It says that outside it is 10 degrees. So out there, the molecules are moving much slower than it is in here, where it is 66.6 degrees. Now, that might be a little hard to grasp. So, to give you an example you can all relate to. You ever been by a fire and gotten way too hot? That's because the molecules in that fire are moving crazy fast. So fast that it is way too hot to be too close to. And have you ever put your hand on something that's metal when it's really cold outside? It feels really cold, doesn't it? That's because the molecules in there are moving much slower. If I go over to my stove and I turn it on, it makes a fire. The molecules in that fire are moving very fast. So fast, I can't get much closer than this. It's way too hot. Now let's go over to my freezer. If I open this up, everything in here, its molecules are moving much slower, and it's not that hot. It's cold. Ice. Molecules are moving very slow. Heat is defined as the transfer of energy between two materials. And it also always flows from the higher temperature to the lower temperature, never from the lower temperature to the higher temperature. If I take a chunk of ice and hold it in my hand, my body temperature is warmer than the temperature of the ice, so it'll melt the ice. You can already see that it's melted part of the ice on my hand and turned it into water. Now you may be thinking, well duh, your hand was going to melt the ice. But you also might be thinking that, well, does it always flow from higher temperature to lower temperature? Didn't the ice also cool down your hand? Yeah, it did, but that's because my hand put the warmth from my body into the chunk of ice. Just the same way that if you're outside on a cold day, you're heating up the air around you. The temperature from your body is going into the cold air around you, and the cold air is taking that energy from you and putting it into your surrounding area. Or if you're hot outside, the hot air is heating you up. You're not cooling it down. You're just heating it up, and it's putting more energy into you. Okay, so there's three ways that heat can transfer between two materials. First one I'm going to talk about is called conduction. Conduction is when two different materials come together and slam against each other. Really, materials doesn't matter what they are. Just as long as they're different temperatures, so that the warmer temperature can flow into the item that has a colder temperature. For example, I'll keep it simple. Go back to my example with the ice. When I grab my ice, the molecules in the ice were slamming against the molecules in my hand. My hand was heating them up. This is conduction right here. Anything that touches each other and changes temperature is conduction, really. So, in turn, wouldn't it work if I really grabbed anything? If I open my fridge, grab the first thing I see, some yogurt. The yogurt is colder than my hand, and the molecules in my hand and in the container are slamming against each other. That's conduction. Now the second one is convection. Convection is the mass movement of molecules across something. If I turn my stove on, there's a flame. Now if I take my hand and hold my hand above that, I can feel the warmth, but I'm not really touching the flame. Why is that? Because the heat from the flame is warming the air molecules, and the air molecules are rising up. So if I just hold my hand above it, I can feel that warmth. Last one's a little tricky. It sounds kind of like convection when you hear about it. It's called radiation. That's what the sun does. The sun radiates its warmth down to the earth. Radiation is when energy moves through waves in light. You can barely see the sun. It's sunset right now. But it's really and the difference between convection and radiation is that when I said convection, I said that the stove was heating up the air molecules around it. And that they were rising. That sound anything different from radiation to you? I'll explain it. With my stove, the air molecules all around the flame are getting very hot, and they're rising. So I can, like I said before, hold my hand here and feel the warmth. Now, that needed a medium to pass through. Medium was really its mode of transportation. For that example, it was the air molecules. But radiation doesn't need a medium. It just travels. Now, there's a couple laws with energy. These are called the laws of thermodynamics. First law of thermodynamics states that energy cannot be created or destroyed. It's called Law of conservation of energy. Makes sense? But I talked to some people and they thought I was wrong. They said that they heard at their local power plant they used hydroelectric generators that took the stream water and changed it into and made electrical energy. They're not making energy. They're just changing the form of the energy. When it was in the stream, the water was moving down the stream. That was kinetic energy, as I explained before. And then the water slammed into those generators and made them spin around. That lost some of the kinetic energy, but put it into the generator. And the generator changed that kinetic energy into electrical energy. So as you can see, they didn't really make energy, and the stream didn't really lose energy. They just changed the form of the energy into electrical energy. Happens pretty often. And the second law states that everything. The second law of thermodynamics states that energy will always flow from the higher temp to the lower temp, and that energy will spread out. Seems pretty simple. So, by this law, it means that if I take some ice out of my freezer and I set it on my counter, in a while it'll melt, turn into ice water, but then that water will go back to room temperature. That's because energy always spreads out. Just the same way that if you take something hot out of the oven, let's say you made a batch of cookies, take them out of the oven and you put them on top of your stove. Eventually, the pan and the cookies are all going to cool down to room temperature. That's the same as all the energy spreading out. The temperature within the cookies was much higher and the molecules moving much faster, and it had heat energy in it, a lot of it. In the room, molecules weren't moving as fast and didn't have quite as much heat energy. But then the cookies flowed their heat to the room because the higher temp always goes to lower temp. It's just all their energy spreading out.